Alright, welcome to would this be the fifth video on calculus? Yep, it would. Alright, we're going to solve some basic derivatives. Alright, and here's one thing that happens. Lots of people, when they teach calculus, they don't really tell you where lots of these facts come from or give you a sense of why they're true. And so I'm going to try to at least give intuition for each derivative that we prove. One time we might prove a derivative using the actual formula. And we could use the limit definition. Sometimes that actually helps simplify the problem. But in essence, that's what we're going to mess with. So that's one way to prove things, but I think that's pretty solid because it's a formula, and so if you work out an answer from the formula, then it should make sense. Your end result should end up making sense. So sometimes we might do that. But another way to calculate derivatives is actually, this isn't perfect, but it's pretty solid. It's by hand. And we're going to try that right now. What is the slope formula? That's what I'm going to ask. This is how you write it. What is the slope of cosine of x? Actually, before we even do this one, let's do sine of x. What is d over dx sine x? Alright, I recommend you try guessing it for a second. First, I'm going to go over this notation. It's known as Leibniz notation. You know, named after Leibniz. Oh, by the way, I forgot to mention, Leibniz, Germany, or like the Holy Roman Empire, that was kind of the zone during the time period. And Newton was part of, well, England. And so I forgot to mention that. It's kind of a small detail. Either way, so derivatives. So why do we write like this? So we said change in y or change in x. We want that to be the slope, but that's kind of a general slope, not the derivative slope. So how do we turn it in the derivative? So we want this change in x to go to 0, right? We want change in x to go to 0. And change in y can be better written as this. It's the f of x plus, well, it's actually a change in x value, isn't it? Because that's the change in x. You always go that change in x if you subtract this. You agree, right? You have this x value, and then the difference between the two will leave a change in x. And so the slope formula still works out. Now we want this change of x to go 0. Rather than writing epsilon, we're going to write change in x go to 0. We're telling it what to do. And it obliges, but either way. So when change of x goes to 0, we know that if we plug in 0, we get a problem. So we want something, this is what Leibniz called the differential or the infinitesimal. Because it's infinitesimal because it's not 0 yet, but it's really close. And of course, we want to, let's put a limit here. All that limit does, since I don't talk about it all that much, is it's just the idea of approaching rather than being at value. It works better with mathematics and algebra when you have a limit. And this limit would stay true for this problem. Change in x to 0. But now, because change of x goes to 0, we have what we call the differential, the derivative. Oh, no, not derivative. The infinitesimal of x. The way I say it is tiny change in x. And this would be tiny change in y. So this is all the same thing, and it's all a derivative. If f of x is the same as y, then this is perfectly true. So all of these are the same thing. And this notation is what we write. Except for rather than writing y, we actually write the functions. Because y, again, it doesn't define the function. It's just an arbitrary thing. It doesn't even tell you the inputs into the function. So let's get going here. So I was just introducing that. So you get where that d is. It's like a change, except for it's an infinitesimal change. It's almost 0, but it isn't because 0 causes problems. All right. So sine of x, how do we find it? So we want to find the slope basically, right? The slope of both of these. So let's do it by hand. So we have our x's. I'm going to draw it like this. So our angle would be here. Angle is what you input into these functions, but we're making x this time. And it oscillates between 1 and -1. I've done this so many times, actually. I'm surprised how many times I've done this in only this many videos. But oscillates like this. Alright? And we know that this point would be pi, this point would be 2 pi, this point would be 0. I don't have to write the rest of these, but I am. 4 pi, and it's also 5 pi. It's a pi. Either way, so that's the sine curve. All right, so I'm scooting this. So how do we calculate the slope? Well, you could do that. You could do this, which kind of sets up a triangle that's infinitely small, but how about this? I said we'd do it by hand, so let's try to do it. Let's try to estimate it. So we know flat parts on curves have a slope of 0, right? So this point would have 0, this would have 0, this would be 0, this would be 0, this would be 0. So let's do that. We actually do this in physics all the time. If you have a graph of a function, you can graph the velocity just by eyeballing it. All right, so ready? So slope here is going to be a flat line, so it's going to be 0. There's going to be 0. There's going to be 0. 0, 0. Guess what? 0 again. So we know that. This has a positive slope. And actually right here, this is an interesting fact, by the way. Sine of x, when x gets close to 0, let's just say x close to 0. I don't know why I wrote it as letters instead of the actual 0. But anyway, sine of x is about the same thing as x. And that's because the slope right here is actually 1. It doesn't look like it, but it is. The only reason I bring that up is because the derivative of this point at 0 is 1. The slope here is 1, and the slope here is actually 1. So x, the line x, if you actually graphed a straight line down here, I would do it in this color, but I don't want to mess with my derivative graph. Either way, the slope is a positive 1 because of this fact. You can check this on a calculator. If you plug in sine of 0.001, you're going to get something close to 0.001. It might be 0.000999, whatever. But you get values close to 0. So that's my only point. So the derivative is about there. So I'm going to just guess it's 1. And this is also true for tangent, if you're curious. It helps also with knowing limits. We're going to do more limit stuff later, but this is just the idea of making the derivative 0, but not directly 0. Wait. So we're going to get 1 here. Now, if this is positive 1, this is going down, so this looks like a negative 1. Positive 1, negative 1. So you get what we're doing? We're kind of estimating by drawing a line at points that seem easy to identify. So up here would be a negative, so -1. And so we're just plotting it. And this is actually a viable method for doing lots of graphs. Look for when it's 0, look for when it's a positive, look for when it's a big positive, small positive, stuff like that. And now, let's connect the lines. And I'm just gonna estimate here a bit. Insane. The slope looks like, what is it? It starts at 1. And at pi over 2, it hits 0. Looks like cosine. In fact, that is exactly true. It is cosine x. Now, you could try this formula. If you tried it, you'd probably be unhappy. I was unhappy when I tried it. So I'll admit it, I kind of gave up with it. Doing it this way doesn't appear to work. I mean, you could probably plug this in on a calculator, just make this epsilon to 0.0001 and just graph it. And it'll get you something close. Oh, and by the way, I meant to do sine. But I guess that's what we do for cosine as well. Yeah, I saw this cosine. I was like, okay, so we're doing cosine. No, we're doing sine. My bad. But either way, you could try that. Maybe there might be some property with what would this be? Trig ratios, but I don't know it. But yeah, and this is actually pretty elaborate. I think this is a really good proof. You could probably do it further and actually try to calculate slopes by taking those small distances and just calculating them one at a time, and then you'll get an overall picture that you get the cosine curve. But I'll just tell you right now, cosine. Now the funny thing is, most teachers and people just tell you cosine and you're good. You're on your way. Just accept cosine. Now this, I think it's far more convincing than just telling someone, it's cosine. So that's kind of the point of me doing this video. Let's do another one. So cosine. We have our cosine curve. Let's get another color we haven't used. Let's do like green. We haven't done green. Slope here, flat, so it's a 0. Slope here, it's a negative, and I'm just going to say -1 because we've kind of did that with sine. Slope here on the blue curve is 0. Then it's a +1. Then it's 0. -1. Let's just, I think we get the picture. Goes here. Then 0 slope here, then am I doing it right? Oh wait, nope. Passes through here. Alright, and we get this cool little shape. Now, it's not sine of x. Sine of x is that red line. However, if you took every point and just made it negative on the opposite side, just made the negative of it, then you'd get this graph. Therefore, negative sine of x is cosine, is the derivative of cosine. And to find derivative of negative sine of x, because of, wow, that's one rule I should cover. All right, before we can, let's continue to the next page, and I'll find the rest. So negative sine, and then what does negative sine get you? And I'll just tell you right now, that gets you negative cosine, because cosine gets you a negative, and negative times a negative is positive, so it gets you back to sine. So it's this interesting loop of derivatives, these tangent functions. Not even ratios. So I'm going to switch pages, and we're going to do some derivative rules. So these are just basic derivative rules that will help you in the long run. So turn the page. All right, so here's another derivative rule. Actually, let's just write it out. If you have any constant, times a function, what is the derivative of it? Well, let's find out. Let's do the limit formula. And I know all of a sudden I started doing the limit, but I like doing the limit. And I could have wrote change in x, but the problem with using that change in x definition, in my opinion, is you have a lot of x's here. How do you know whether it's change of x or not? It's kind of a little hard. Of course, it's just the triangle, but you try it. It gets complicated, or at least complicated me. So you have a times, and then you plug inside of f of x, the x plus epsilon. That's what you do there. Then this is a times the f of x, just plug in x. And then you subtract by the two inputs. The input here is just x plus epsilon. And then the input here is x. I didn't have to do that. These cancel out. Alright, so you get epsilon on bottom. So notice something. This has an a in it, this has an a in it. So you can factor it out. So this is the limit of a times, I could put the limit inside of it, but a times f of x plus epsilon minus f of x. Do you agree? A factors in, so a times this and a times that. And then there's just any number, really. And then it's divided by epsilon. Now you could bring this limit forward, just, switch place. Because a is not part of the limit. All you care about is when epsilon goes to 0, not when a goes to 0. So you can bring it out. Now we're almost done. F of x plus, that'd be epsilon in this case, minus f of x, we're on the edge of the paper, and divide by epsilon. Now what is that? That's the definition of the derivative of f. So it's a times f prime of x, the first derivative of x. And by the way, if you get more derivatives, you put more slashes here. So that's all it means. If you take a derivative of this again, you'd get a times f double prime, whatever. So what does this mean? This means that So this derivative, any number times any function, as long as it's just a constant, you can basically factor it out of the derivative, because this is still the derivative. So here, let's rewrite it in. So it's just clear what we did, proved, showed. The derivative of a constant times f of x is equal to, well, a times the derivative, I'm going to write it in derivative form, of x of f of x. Let's use this in principle. So what's the derivative of negative? No, we got negative sign, didn't we? Yeah, we got negative sign on that first page. What's the derivative of that? Well, we know the derivative of sine. We just showed that. That was cosine. So, here. So our constant in this case is -1. It's -1 times sine. -1 is just a number. So the derivative of negative sine should be negative cosine. And it'll probably check out, just looking at it. Well, what did I do? Oh, everything's off kilter now. Oh, there we go. Yeah, if you look at this, is it the green graph? Yep. If you look at the green graph, the slope here is 0, and slope here would be negative. So just be a flip cosine. But using this formula makes the math work out. Like, it just works out perfectly. And this is, I don't know what I'd call it. I think it's like multiplying. What else? Well, take the derivative of negative cosine. Factor out the negative. What's the derivative of cosine? The derivative of cosine. So I'll just put the negative on that side. But we know the derivative of cosine is negative sine, so you get negative sine times -1, basically. And -1 times a negative is a positive, so you get positive sine. I didn't have to put the -1 on that side, I just did because that is what this rule states. It comes in really in handy. And that's why when you got those old formulas, like the derivative of, man, I wish I could write this faster. Anyway, that's why in x squared, cx squared, you got c times 2x. I know I wrote it 2cx, but whatever. That's because the derivative of x squared, which we technically solve for, is just 2x. So it's going to be 2x times c. That's why that made sense. And then the last thing to show that we already showed, we don't have to, the derivative of any number, as long as it's a number that doesn't involve x, it could even be a function. If it doesn't have x in it, doesn't matter. The slope of it, with respect to x, that's what we say, with respect. That's what we care about in this case. It's 0. Always. Always, always, always. Anything else? All right. I'm going to push this one more video. And then we're going to connect the ideas of integrals and derivatives. And next video, this should be a really cool proof with Pascal's triangle that we already used. So this is going to be awesome.